Hi again everyone, I'm Chris Tisdell, and in this presentation I'm going to give some basic new research results concerning dynamic equations on timescales. Now the nature of this talk is reasonably elementary. This is more sort of a bit of fun for me, some ideas and concepts that I've just been having a very enjoyable time playing around with, and it's fun for me, and also I'm very confident that the level at this talk will be understandable to advanced undergraduates or people who are just looking for what basic research in mathematics can be about. Okay, so my presentation is about dynamic equations on timescales, which is just a generalization of the ideas of ordinary differential equations and difference equations. And I'm going to define what I mean by an exact dynamic equation. Okay, so I guess there's three or four main points to this presentation. Firstly, I am going to introduce the idea of an exact dynamic equation and an exact linear dynamic operator. And what this means is that the equations, the general equations under consideration, can have their order reduced. Therefore, the analysis and the solution method will simplify. Okay, so that's the significance of the results. Now, I'm also going to go a little bit further and introduce a condition that's both sufficient and necessary for certain classes of second order problems to be exact. So that's a reasonably powerful result. And later on, after I've gotten through these preliminary concepts, I'll apply the ideas to solve exact second order dynamic equations on timescales where the coefficients may be non-constant. Okay, so this makes it a little bit more difficult. Now the ideas in this presentation are related to those of Bonner and Peterson's very famous book, and I think the results there in section 3.4 and the results that I'm going to show you today kind of complement each other nicely. In some sense, they're talking about the method of factoring in section 3.4, which is kind of a little bit more general than what I'm going to talk about today. But on the other hand, my results are more general because they only consider second order problems, and my ideas and concepts relate to a whole range of problems. Okay, so here is my definition of an exact second order dynamic equation on timescales. Okay, so we say that a second order linear dynamic equation, equation 1, is exact if there is a function f such that the left-hand side of 1 is just the derivative of what's inside, the delta derivative of what's inside the brackets. Now, of course, to understand this notation, you'll need to know a little bit about timescales and dynamic equations on timescales. Now, if you don't know anything about those areas, just think of these deltas as derivatives, okay? And you can forget about the sigma here. Now, the t, I do have another video which gives all the basics of timescales and dynamic equations on timescales. So, if you want to go and get some background on the notation here, then I'll put a link to that in the video. Now, just to give you a little bit of background here, for those of you who just want to keep going, I guess the domain of these functions and the unknown solution is a timescale, which you write like that, where the set t is a closed non-empty subset of the real line. Okay, and the x delta is a generalized derivative, okay, of a function x, which is defined on this timescale. Now, you might be looking at these x sigmas and wondering what that represents. Well, x sigma is just defined to be the following, I guess, combination of functions, x of sigma, where this function sigma just maps the timescale back into itself, and it's known as a forward jump operator, forward jump function. And for any point in t in the timescale, sigma of t is just the point immediately to the right of the point t. Okay, so for example, if the timescale is the real numbers, then sigma of t is just equal to t. If the timescale is, say, the set of natural numbers, then sigma of t will be t plus 1. Okay. Now, if the timescale is the real numbers, then this equation is just p of pt x double prime plus qt x prime plus rt x equals g of t. Okay. If t equals the say the natural numbers or the integers, this is p of t plus 1 times the the second forward difference of x plus q of t times the forward difference of x plus r of t times x of t plus 1 equals g of t. Okay, now let's get back to the actual definition. We say the second order linear dynamic equation given here is exact if we can produce a function f such that the left hand side is equal to the derivative of this. Okay, the delta derivative of this. Now, first of all, you may think, why have I got a minus there? Why not a plus? Well, you could have a plus there. Why I've got a minus there will become clear a little bit later. It has to do with, I guess, using a quotient rule rather than a product rule in the calculations. Now, many people study exact ordinary differential equations in a first course in differential equations. Okay, it's a little bit different here. We're using a linear second order problem, but the idea is the same. Essentially, what it means is you can break part of the differential equation down to the derivative of something else where you've reduced the order. Okay, so P, Q, and R and G are all functions in this setting, and the challenge is to produce an f or show when an f will exist, such that the left-hand side and the left-hand side of this, it can be sort of compressed or reduced to this. Okay, so when is that possible? Well, this is one of the, a reasonably nice result here. I've called it a theorem. It's probably a lemma, but the dynamic equation 1 is exact if and only if the coefficient functions, or I guess the P, Q, and R, satisfy this equation here, equation 3. Okay, so this result is both sufficient and necessary. Okay, so it's a very powerful result here. Okay, so I'm going to prove that. Now, throughout we're assuming that all these delta derivatives exist, but I just haven't really noted all that down. Okay, so I'm just going to prove this. So we need to prove it both ways because it's a if and only if statement. So let's assume that 2 holds. Then you want to show that 3 holds, and then we'll, later on we'll assume that 3 holds, and we want to show that 2 holds. Okay, so if 2 holds, what I'm going to do is write this out and expand this using just the regular derivative expansion, distribute the delta derivative, and then use the product rule. Okay, so if I expand the right-hand side, I can use a little bit of the product rule and then sort of put things back together. Now, there is a special product rule for the timescales calculus. And this is what I get. Now, so I've sort of, done 2 steps at once there. Now, what I want to do is essentially equate the coefficients between the 2. Okay, so, obviously they're the same. I want that to equal that, and this to equal this. So equating the coefficients, we have, all right, well, that's not very interesting. The second one is more interesting. Okay, now, if I take the delta derivative of this equation over here, and then I can replace the resulting negative f delta with r, then I'm going to get 3. Okay, so I can just replace this with r. Okay, so that's one way of doing it. So now we assume that 3 holds, and we want to get back to 2. Now, let's choose. I'm going to choose a f defined by this, p delta minus q. Okay, so we're choosing f to be that. So if I take the derivative of this, delta derivative, I'll get the following. So let's work with this right-hand side for this particular f. Now, I'm actually not going to write that f down here. I'm just going to keep it a bit more compact. But this is the f that we're talking about. Okay, again, expanding using the product rule, I can come up with the following. Okay, now, if I replace f in here with this, and if I replace f delta with this, then you can see this is going to cancel out and I'm going to get a Q there. And from 3, this is going to be negative R in the brackets here. So I'm going to get negative R, which will be positive R. So, two holds. Okay, so I've proved that both ways now, and that's the end of the result. Now, condition 3, for those of you who've, say, done a second course in ordinary differential equations, this may look familiar. It's actually a generalization of the adjoint equation when you study linear problems in a second course in ODEs. So this is kind of nice because it's a more general equation, and it simultaneously encodes ordinary differential equations and difference equations and everything in between. So here is a result that lets you take a second order problem that I showed you at the start and form the solution. Okay, so if problem 1 is exact, then the solution x is given by this representation here. Now, here the integral is the delta integral, okay? So it's like the opposite of this general delta derivative. Now, t0 is an arbitrary point in the time scale. The constant c up here is this. Now, the e sub f on p is like a general exponential function. Okay. Now, some things that we're including in there. This ratio f on p is assumed to be regressive. Okay. So this is a sort of a property involving the timescale itself and the functions f and p. Now, I don't want to talk about that too much, but this is just so the exponential functions are well defined. So let me show you how this comes up, just briefly. So since our problem is exact, we can sort of compact it. We have so there is some f such that we have the following. So I can, form a delta integral on both sides, say integrate from t0 to t, and so I get the following. Okay, so if I integrate both sides from t0 to t, then that'll be my first term, and using this c here and just rearranging it, I'll get the following. So let's go with dummy variable s here. And then what I can do now is you can see essentially I can rearrange, and this is essentially a linear dynamic equation now, first order. Okay, so if I just sort of divide this coefficient out, so I'll get the following. Okay, and now using an integrating factor here, I can compact this left-hand side down to the derivative of a special quotient. Now here I'm using the quotient rule because I've got a minus sign there and no sigma there, but there are variations on this. Okay, so I've so this involves essentially the quotient rule. Okay, so now what I can do is I can take the delta integral of both sides, and then just bring this exponential up to the other side. So I'm not going to put those details in, but it's pretty easy to get back to 4 from this. Just integrate and rearrange. Okay. All right, so let's look at the more the wider case now. I guess I've looked at second order problems, but you can define linear dynamic equations of nth order, for example. And to do this, I'm going to involve dynamic operators. So we call an nth order linear dynamic operator exact. If there is another linear operator that is n minus 1th order, m, say, such that L is equal to the delta derivative of m. Okay, so, for example, what we were doing before, here L is the left-hand side of this, and m would be what's inside these brackets. So L's second order here, m's first order. But you can define these things for more general cases. Okay, so let's look at an example, another example. Here's a linear dynamic operator. If you rearrange this, you'll get what's known as the Cauchy-Euler type equation on for dynamic equations on timescales. And the claim is that this linear operator is exact. Now notice there's no sigmas here or anything, so this is a slightly different operator to the one that we looked at in the first few slides of this presentation. Okay, so what we want to do, we want to come up with a linear operator m that's the first order, such that this is true. So let's call this double star. Now, so if I look at this, here, what I can do is actually, with a little bit of work, is rewrite it in the following form. Okay, if you sort of distribute this and use the quotient rule over here, you'll get back to that. Okay, so this, what's in the brackets here, will be our linear dynamic operator m, which is a first order. Okay, so we'll conclude that our L is exact, because we've come up with another linear operator that's first order, such that the delta derivative of this equals L of x. Okay, so that's the end of the presentation. Here's a couple of references. Here's Bonner and Peterson's very famous book. Here is the introductory video on dynamic equations on timescales. You can either go to my YouTube channel and find that, or you can try this link here. And there are a couple of other references that I haven't listed, but kind of helped me out a lot with this presentation. I actually thought about the idea for exact dynamic equations on timescales while I was reading Boyce and DePrima's famous ODE book. There is another book on difference equations where they do talk about exact difference equations. This is by Levy and Lessman. So there are some references for you. I hope you found this presentation useful, and look forward to more presentations on YouTube in the future.